Hello and welcome to How to Become a Rocket Scientist, Part 3. Today I'll be covering the topic of orbiting satellites and geostationary satellites and a little bit of the calculation of math. In particular, interesting result is we're going to figure out why geostationary satellites always seem to have the same altitude in the sky. So I hope you enjoy this. This is brought to you by my own company, dspwidgets.com. We don't really sell anything of interest to the individual consumer, but I thought you might be interested and want to go over to www.dspwidgets.com. I hope you enjoy. Okay, let's get started. Today we're going to talk about satellites, and imagine that you have a satellite and it orbits the Earth. Round and round she goes, and you can see that this circular motion, you can think of this as like having a mass or a tin can at the end of a string, and you're spinning it above your head, and you know from having done that the tin can will fly out as far as the string will let it, and it will pull the string taut, and therefore you should think about this as that the tin can is putting a force on this string, and that's because of the rules of inertia and the properties that we've observed before. But we know that from Newton's law that an object once in motion will continue in motion in a straight line unless forces act upon it. So the thing is that tin can, once it gets up to some speed, wants to fly off straight. It does not want to go in a curvilinear circle. But what's restraining it is the string. And so the string, right here, the string S, has to exert some force on the tin can to pull in a course correction at every moment. And this arrow is confusing because it was correct when it was the only arrow in the picture, but the direction of motion here constrains me to look more like this. So at any instant, if the string broke, the can would fly off like this. This should be perpendicular to the string. It's not quite. But instead, we want to constantly pull it into an arc, and so that requires a little bit of a course correction. Now the thing is, this is where vectors and not scalars become important, is that this course correction changes as it goes around the circle. There's a small course correction in this direction, but when the object gets down here, there's a course correction in this direction. And so you can see that correction vector changes, and that's why that vector is not a constant velocity, it's a acceleration. So here's the thing. Another thing about vectors is that you can imagine this arc or circle as being drawn around the equator. Well, what would happen if we tried to make a little halo around the Earth? We had a nice little orbit, but it's not at the equator. It's north or south of the equator. Well, the problem with this is that if you don't orbit with the center of the Earth in the center of your orbital circle, you end up having a problem. And that problem is that if you look at this sideways, where here's your Earth and this is the satellite up here, that the force of the circle that needs to hold it in a circle is going to be pointing this way. But the force of gravity is going to be pulling the object in this way. So you need these two to line up and be the same. So I got a little ahead of myself. So what do I mean by all this? Well, an object is in orbit when the force of the centrifugal force making the object want to leave the circular orbit, or the force pulling against the string, if you will, matches exactly the force of gravity pulling down on the mass. And so in this case over here, the force of gravity would pull like this, and I've really shown the arrow in the wrong place. The centrifugal force of the mass is that way. So you want these two to be directly opposite and equal, and they're not in this case. And so what would happen is obviously the orbit would correct, but the orbital speed would change, and so would the velocity. I'm sorry, the orbital speed would change, and so would the altitude. So, okay, so you can I think you can grab that there's a force of gravity pulling in, and a natural force of centrifugal force wanting to pull that can out, which is really the same way as saying that this is how much force you have to pull in to keep the can in a circle. And so we now have two well-established equations. So the force of gravity, we've already seen, is equal to gravity constant times the mass of the Earth times the mass of the satellite over r squared. However, this force of the can, or the satellite, pulling against the so-called string, what would that be? Well, there's another well-known equation. That force is equal to mv squared over r. I shouldn't make that cap because it's confusing. Now remember that the magic Newtonian equation for acceleration and force is F equals ma, and notice that this part these two equations look a lot like each other, and so we say that this v squared over r term is the acceleration required for centrifugal force. So if we want to have an orbit, we can see that this force here must equal this force here, and they must be equal and opposite vectors. And we didn't express this as vector mathematics, but that's okay. We'll just deal with the scalar, and we'll keep in the back of our mind that, hey, we have to have these forces line up, so that means an Earth orbit around the either the equator, or at least it could be this way, as long as the center of the Earth is in the center of our orbital circle or ellipse. So, so we're going to set these two equal. GME ms r squared equals m, what mass? Well, that's the mass of the satellite, v squared over r. Now I want to point out a very interesting property here, and that's that this force changes it as the square of the distance. It gets weaker the larger the radius goes, but it gets weaker by the square, whereas this one only gets weaker linearly by the distance, but it gets weaker by the square of the velocity, or it gets stronger by the square of the velocity. So that's an interesting relationship, and we'll use that perhaps in another lecture. So right away we see these terms cancel, and we see that we can get rid of this and get rid of this. So we're left with the result that v squared is equal to GME over r. Okay. So this result here shows that if we speed up our orbit, we have to get closer to the Earth, which is an interesting result, because as r decreases this side we get bigger, which would keep this equation in balance. So to stay in a stationary orbit, if we want to go faster, we have to get closer. So this makes sense from a solar system point of view, because we know that the planets in larger and larger radiuses take an enormous, away from the sun, take an enormous time to circle the sun. And planets close in zip around that sun very fast. So let's talk about this term. So we could plug in several values for r and v squared, and then we would know the altitude from r. Remember, r is just the radius of the Earth plus whatever altitude we have. And so, but that would be rather uninteresting. All we would get is sort of like a table. But what I want to do is try to figure out what happens when you have a satellite, and in this case we want it to be around the equator, but we want it to go at a speed that equals the rotational speed of the Earth. That has a very nice advantage that that the satellite would track the Earth and stay in the same position in the sky with respect to an observer on the ground. And this is exactly what happens with a lot of communication satellites. And they're designed so that they are in the same position of the sky all the time with a given position on the ground. This makes it very convenient because when you go out and you get your DirecTV satellite dish and you put it on your house, you can do the initial calibration, point it in the right direction one time, and then hopefully not have to revisit this unless your house moves considerably, which, by the way, if you have a travel trailer and that's your house and your dish is on top of that, you're going to have something to gimbal or correct that satellite's pointing direction as you drive down the road. Or you can just simply decide that whenever you make camp, you're going to have to climb up on top of the roof and readjust that dish. So, so here's the thing. This then determines the speed if we're going to say we're going to match the planet's orbit. So we know that speed is equal to distance over time, and we can figure out the vector speed, which we're going to then substitute for, the scalar speed, which we're going to just ignore vectors and scalars, and we're going to use velocity and speed interchangeably. So the only difference between the two is velocity has a given direction and speed is just a scalar quantity. So the distance here is going to be the radius of the Earth plus the altitude, which we've used as r up here. So the distance is going to be r, 2 pi r. This is the distance around our orbit. It's pretty basic math. Distance around a circle is 2 pi r. And we're going to divide that by the time that we want that satellite to travel that distance. And that's going to be equal to 24 hours, more or less. So it's going to be, but keeping the units consistent, we need the units to be in seconds. So we're going to say 24 hours times 60 minutes in an hour times 60 seconds. Okay, so that's our velocity that we're going to need to have for a geostationary orbit satellite. So we put all this back into the equation, and what we get is kind of a big mess, but we're gonna call, just for now, we're gonna call this part of the equation, we're just gonna give that a constant k. So we don't have to do the math right now. So we're gonna say that v squared is equal to r over k squared, quantity, must equal g mass of the Earth over r. So simplifying this again, we can see that if we move the r up here and the k down here, we get r cubed is equal to GME K squared. So this will allow us to determine the necessary altitude for a geostationary orbit. Notice that the velocity doesn't appear. Nothing else matters, because in order to be geostationary and to be in orbit, you have to balance your altitude and your speed out so that the forces counteract. And so what happens is that we're just left with this R value that we can compute. So we see that also that the mass of the satellite doesn't matter, it's just the mass of the Earth. So basically what I'm telling you is that any geostationary orbit around the equator is going to have the same R value. That's an important result. And so all of the satellites that carry communications that want to be geostationary have to be at this particular specific altitude. Okay, so what is that altitude? Okay, I'm back, and you can see some magic constants appeared up here that we're going to need up in the corner of the screen. So there is an error, however, that I have discovered. So if we treat this as the quantity k, then what we need here is not the quantity r squared over k, but rather times k. So my apologies, this was an error. So to correct that, we have to do k r squared. And you can see I've computed k squared up here, and y squared, well, you'll see in a moment. So this whole thing gets changed as well. And the k would be squared as well. Has to be, because this substitutes for v squared. So this is the velocity, which is rk. So velocity squared would be k squared r squared. Okay, so then we simplify this equation, and now we get the k squared term down here, which is very important for a correct result. So what's our answer? Well, our answer is for r cubed, when we compute this, is a nice large number. Let me get r, because we don't want r cubed. So this is one of those rare cases in math where you actually need the cube root of something. And I get the answer, r is going to equal 42,258,000 861 meters, or 42,258,000, we'll chop off the rest, kilometers. That's the orbiting altitude that is required. And if you do this in terms of miles, you would take our constant that up at the top that says 1 mile equals 0.6309 kilometers. So we multiply this by 0.6309, and we get about 26,661. So it's about 26,661 miles, but that's from the center of the Earth. And so the Earth being roughly 4,000 miles in radius, we observe that the orbital altitude is 22,661 miles. And I happen to know that that result is roughly correct. So Um, I can see it went off screen. So let me write it again. It's correcting for the Earth's radius. It's about 22,661 miles in the air, altitude. So that's a very good result. A lot of these numbers have been crunching with my DM42. You can find this on Amazon. I'm not really advertising it per se. I'm just telling you I like it. It's based off the HP42. But the nice thing about this, especially for rocket science, is that it has huge precision and it has huge range, far greater than you'd ever see in a normal calculator. So I can calculate numbers with like 55 digits of decimal precision behind the radix, and powers up to like 230 something, 10 to the 230. So that's a pretty big number. So with still pretty good precision. So nice calculator, but that's neither here nor there. Okay, so what we've shown is that we can calculate the orbital velocity given an orbital altitude, or the orbital altitude given an orbital velocity, or we can determine how to make a geostationary orbit and compute the altitude from that, because the velocity is determined now both by the orbital altitude and the rotation of the Earth's speed. So I want to point out that there are other orbits possible. So we talked about orbits that don't go around the equator. These are very useful orbits for things like GPS satellites, which have to have a fairly low altitude in Earth in order to be able to pick up a signal with a pocket-held and handheld device. You wouldn't want to have to carry around a cell phone with a DirecTV sized dish antenna on it. That would be rather cumbersome. So those satellites orbit at a much lower orbit, but as a result they can't be geostationary, and to have good coverage at all times they have a constellation. They have several GPS satellites, plus you have to be able to triangulate on a few at any one point in time to get a fix on the Earth. So anyway, I hope you enjoyed this. This basically is all I have to say at the moment about geostationary orbits and computations involving them. Hope you have a good day. Thanks for watching.